conservation of linear momentum. The law of the conservation of linear momentum. The rule of this, the conservation of momentum, is that the total momentum before collision will be equal to the total momentum after the collision, provided there are no external forces that have been introduced. If the net external force acting on a system is zero, the total momentum of the system remains constant. This was taken from the November 2004 mark scheme. If the total external force acting upon a system is zero, then, in other words, for an isolated system, the momentum of the system is going to remain constant. This is from the May 2005 mark scheme. So this is a question which comes up quite often. They ask you to define this, and there will be 1 or 2 marks going for it. The total momentum before collision equals the total momentum after the collision in an isolated system. So here we have an example here. We have mass 1 and we have mass 2. Okay. What's going to happen is that before the collision, mass 1 is moving and mass 2 is still. So mass 1 collides into mass 2. Then afterwards, and what we have, the total momentum before is equal to the momentum of mass 1, which is m1u1, m times v, remember, and the momentum of the second body is m2u2, which is, so the total momentum before is the sum of each of the momenta of these. After the collision, some of the momentum of the first one will be transferred to the second. So this happens. Afterwards, the two bodies move off. Each one has a different momentum now. The final momentum, m1v2, v stands for the final value of velocity, and this is m2v2. Now, for this to be constant, the sum of the momenta before is equal to the sum of the momenta afterwards, and that can be expressed like this. This is the conservation of momentum in algebraic terms. Okay, let's look at some examples of collisions and how we can do the calculations with momentum. A sticky collision is when one body meets with another one and they stick together. Let's put some values in here. Let's say, for example, that the masses are equal. The first mass arrives with a velocity of 6 meters a second. Its final velocity we'll find out. The velocity of the second body, which is still, is 0, and we know that VB is equal to VA. How do we know they're going to be the same? Because they stick together, they move away at the same velocity afterwards. So we just need to put these terms in. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the initial mass. This is the mass of the first body times by its initial velocity. This is the mass of the second body times its initial velocity, which is still, so it's 0, is equal to 2 times whatever the final velocity is, plus 2 times the final velocity for the second one. These have to be the same value for v because they stick together. So algebraically we try to solve that, and this is what we end up with. They both move away with a speed of 3 meters a second. Another example of a collision is called an explosion. Kinetic energy is not conserved. In other words, it's not an elastic collision. So if there was some kind of dynamite between them, or a spring or whatever, which forces A to go to the left, B to go to the right, the momentum nevertheless will always be conserved. So this is the momentum equation. the conservation of momentum, the momentum before equals the momentum afterwards. Initially, the velocity of this one is 0, the velocity of this one is 0, so these terms on the left-hand side will always be 0. So ma va plus mb vb. Notice I've substituted a for body A now, rather than body 1. So we know that this must be equal to this. However, not strictly speaking, because this will be 0. ma va will be actually equal to negative mb vb, which means that we're going to have a negative answer here. Mass is not negative, so one value of the velocity will be positive, one value will be negative. And that's fine, because we know that one is going to the left, one is going to the right. Remember that velocity is a vector, it has direction. And in one dimension, we express the vector quantity by its sign, in other words, positive or negative. A little bit of manipulation here, and if you know any of these parameters, you can work out the others easily enough. Okay, here we have a worked example. This is a gangster hit from the 20s. Notice how I write gangster. This is how it's spelt nowadays, apparently. So the car arrives. This gangster on the right, not the gangsters in the car, but the gangsters on the right, is standing in front of a shop window, a huge shop window, and as we all know, they fire the bullet, it hits the guy, and he gets thrown back through the shop window, and glass goes everywhere. You've seen this in the films, and this is what's going to happen. But it's a movie mistake. It can never really happen, and we're going to look at that now. So, bang! They shoot the guy. Where he goes back through the window. He goes flying back, glass everywhere. So, let's look at the momentum aspect of this. The bullet fired weighs 10 grams. It's fired at around 500 meters a second, which is a generous value for the speed of a bullet. The gangster weighs 80 kilograms, and he goes flying back through the window. At what speed will he actually be thrown back? The conservation of momentum, the total momentum before is equal to the total momentum afterwards. M1 is the mass of the bullet, 10 grams. U1 is the velocity of the bullet, 500 meters a second. M2 is the mass of the second gangster. U2 is the initial velocity of the second gangster, which we know is 0 because he's standing still. This will be equal to the final momentum afterwards. Now, one thing that we do know is that, let's say the bullet sticks into him and doesn't shoot through his head and go behind, splattering blood everywhere. There's a sticky collision. So let's put these values in. 0.01, because this is 10 grams times 500, is equal to m1 plus m2 times v2. Notice that this velocity is going to be the same for both bodies because they stick together. You know that what m1 is, that's the mass of the bullet. m2, that's the mass of the gangster. So we put these values in too, and we end up with this. So the v2 is basically going to be 5 divided by 80. Now you find out that that's going to be a very small number. It's a few centimeters a second. Not as we are led to believe in the films where he gets thrown back at 2 meters a second through the glass window. That's not going to happen. It's a violation of the law of momentum, the conservation of momentum, and the law of the conservation of momentum is never broken. In all contexts, at all speeds, the conservation of momentum will always hold true.